I'm Anil Kumar. Welcome to my series on rational functions. In 5.2, we'll learn about quotients of polynomial functions. Now that is how rational functions are defined. To look into the characteristics of these functions and to see how to sketch them, we'll take these 5 examples. So once we understand them, we'll understand most of the concepts related to rational functions, which are defined as quotient of polynomials. After that, we'll take a few questions on sketching graph from given conditions. These are the 4 questions which we will discuss. So you can actually pause the video, copy these questions, try them out on yourself. Let's look into the rational functions and understand the basic concepts. Now, basically, rational functions are defined as, let me define rational function, as a ratio of 2 polynomials. So something will be in the numerator and something in the denominator. And of course, denominator is not equal to 0. Now, this denominator, if it is 0, then what happens? Then there could be 2 things. So if the denominator is equal to 0, then we could have 2 conditions. One, we could have vertical asymptote, and the other, we could have a hole, right? So in this condition, we could have vertical asymptote, or we could have a hole. Now, when do you have vertical asymptote and when do you have hole? Now, if denominator is 0, then hole is there only when we have common factor. In numerator and denominator. Right, so that is the only condition. Now, from the given conditions, this particular equation here, x squared minus 4 could be written as x plus 2 times x minus 2. So x plus 2 and x plus 2 are common factors. So we'll have a hole in this condition, but in other cases, we'll have vertical asymptote, right? I'm not sure about these. You'll have to check whether x plus 2 is a factor of these or not, right? But from the first 3, we can say that there is hole for this particular equation, right? So that's first thing. Second, we could have horizontal asymptotes. Now, horizontal asymptotes we could have in 2 conditions. Condition 1 is when degree of denominator is higher. If degree of denominator is higher, then the horizontal asymptote is y equals to 0. Is it okay? Now, which is the case here? You see degree of denominator is 2, that of numerator is 1. You have horizontal asymptote y equals to 0. Is it okay? Now, if degree is same, of numerator and denominator, in that case, we have y equals to leading coefficient ratios an over, we are saying n numerator, ad denominator, leading coefficients, right? So for example, in this case, we have same degree, 1, 1. So the horizontal asymptote will be y equals to 1, right? So that is what we're trying to say, correct? So that's what we mean. Okay, now one more type of asymptote is there, which is called oblique asymptote. Now, oblique asymptote is possible if Let me write down in a different color. Okay, let me write here. Squeeze it. If degree of numerator is 1 more than denominator. Correct? So the examples would be these. So we have oblique asymptote here. So write oblique asymptote, oblique asymptote. Since these are 1 degree higher, okay. Now in this case, we will see this is kind of very different kind. So that is possibility, right? If degree of numerator is 1 more than denominator, we may have oblique asymptote. For example, this is, we'll just see whether it has or not. Okay, so that is what we're trying to say. So let me summarize here. In this particular function, since the degree of numerator and denominator is higher, the horizontal asymptote will be there at y equals to 0. Okay, now in this case degree is higher for denominator, so y equals to 0 is going to be horizontal asymptote. Is it okay? In these two cases we have oblique asymptote, right? Once you have oblique asymptote, you cannot have horizontal asymptote. Is that clear, right? Now as far as the vertical asymptotes are concerned, let's talk about them also. So vertical asymptotes, here we have x equals to -2, since it gives you a 0, right? In this case, we have at x equals to plus minus square root 2, since that will give us 0. We are not talking about these since we have to factor to figure it out, right? So we're just taking these 3 examples. Now in this particular case, we are going to have a whole at x equals to 2 minus 2, since there is a common factor, correct? So I hope all these things are clear. Now let's take these functions one by one and then understand what are the characteristics of rational functions and how to sketch their graph. Okay, so let's begin with the very first example, which is x over x plus 2. To sketch this particular function, what we can do is we can begin with the vertical asymptote. Since denominator is 0 at x equals to -2, we say x is never equal to -2, right? Now x plus 2 is not a factor of numerator, so there is no question of whole. However, in this case we do have a vertical asymptote, right? So that is the vertical asymptote. So this vertical asymptote will be there, and its equation will be x equals to -2, right? So this is at -2. That is to say that the function will approach this but will never be there, right? Now to sketch the graph, what we should look into are x-intercept and y-intercept. These are easy points to find. X-intercept means somewhere on the x-axis, correct? So that is to say that y is equal to 0. Now in this case, clearly y will be 0. That means x is equal to 0, correct? So we have x-intercept at the origin itself. Okay, so x equals to 0. Y will be 0 when the numerator is 0, correct? Now to get the y-intercept, we have to write x equals to 0, and in this case that is equals to y equals to 0. So that is the common point. Now think about what happens when x is very large number. When x is a very large number, in that case, when we say y equals to x over x plus 2, that becomes approximately equal to x over x. Since x is very large, right? So it approaches this, which is just 1. Do you get an idea, right? So this happens. Even when in this case, x approaches negatively large number. X is a very large negative value. So in that case also y approaches 1. So we are saying approaching, correct? So approximately equal to. So it's basically, in other words, we use the word approaching. Correct? It is never 1 because you cannot be at infinitely large value. This is not a real number. So we are approaching. You get an idea. So that indicates that we have a horizontal asymptote at x equals to, y equals to 1, right? So this y equals to 1 is the horizontal asymptote. Approaching negative or positive infinity is on the left side or right side extremes, right? Now if you take few more values of x, for example, if I write, now we can make some table of values. So what we could do here now is that we will write few values of x and calculate y. So x could be good values to take us close to -2, right? So we could take either side. So let's take -3 on the left side and let's take -1 on the right side. Then what is y value? If I write -3 here, I get -3 divided by -3 plus 1. Correct? So what I get here is -3 divided by -3 plus 2, which is equal to how much? So -3 divided by -1. Okay? So which is equal to 3. Now, if I write x as -1, in that case, you can calculate this as -1 over -1 plus 2. Now that is equal to -1 over plus 1, which is -1, correct? So at -1, I expect a value to be, let's use a different ink. At -1, we expect a value of -1, right? So at -1, we expect -1. At 0, we already found, and we know that the function is approaching this. You cannot cross a vertical asymptote, so the graph will be kind of like this. Does it make sense? On the right side, at -3, we calculate the value to be +3. So from the symmetry about this axis, which is the vertical axis, that is how the graph is going to look. Correct? So at present, we are not getting into a lot of details of this sketching, but with few points, you can see that that is how the graph is going to look. So I hope that makes sense, right? So what we also see here is that this kind of function has horizontal asymptote, which is the ratio of these two, which is y equals to 1. Vertical asymptote when the denominator is 0. X and y intercepts at the origin. And if you take few values, you can see that graph is kind of as shown here. Is it okay? So that is how we do it. Now, you could always take some values which are much closer to -2 from both the sides to get some points here, right? So that you could do after taking few points, take some, but that gives you, whatever I've drawn, a fairly good idea of sketching it. So I hope that helps. Now let's take up the next example, which is we have x squared minus 4 divided by x plus 2. Now let us see how to sketch this function. So this is our rough sketch of x and y coordinates. The function given to us is y equals to x squared minus 4 divided by x plus 2. We could always write this as factored form, x plus 2 times x minus 2 over x plus 2. And now we could simplify and write this as equals to x minus 2. Now this is what we get when you cancel these two factors. But remember, as soon as as these factors are cancelled, we have to surely write that x is not equal to minus 2. So that is a must, because the given function is actually not x minus 2. It is x minus 2 where x is not equal to minus 2. Correct? So what happens at minus 2? So we have a hole at x equals to minus 2. Correct? That is the whole idea. So when you sketch the graph of this function, you have to take care to show the hole at x equals to minus 2. So let's rewrite. So we have y equals to x minus 2 where x is not equal to minus 2. But if I substitute minus 2 here, what do I get? For x equals to minus 2, I get what? I get y equals to minus 2, which is minus 4. So that means this is the position of hole. So hole is at minus 2, minus 4. Does it make sense to you? So x cannot be minus 2, but at minus 2, we are going through a hole which is minus 2, minus 4. Perfect. So basically, in this particular case, we are going to sketch the graph of y equals to x minus 2, where at x equals to minus 2, there is a hole. Okay. So x means minus 2 means y-intercept, x means one slope, right? So it's kind of a line which is kind of like this, right? So that is how we are going to sketch our line. And we have a hole. So let's say this is minus 1 and this is minus 2. Then at minus 2, we have a hole. You understand? Whose y value is minus 4. So the sketch of the function will be like this. So it's a straight line where x cannot be equal to minus 2. Do you understand this? Now it is kind of important to note a very important thing which we learn is degree of numerator is 1 higher, right? Degree of numerator is 1 more than that of denominator, right? Still, we do not have oblique asymptote. Right? So this is very important to note. You may have oblique asymptote if the degree of numerator is 1 higher, right? But these are exceptions. You have a hole here, right? So in this case, you will not have. We are not approaching anywhere. We are already on the line, right? Since you see, we are not approaching. We are on the line. Do you understand? We are not approaching on the line y equals to x minus 2, right? So I hope this concept is clear, right? Now this is very important to understand because in many multiple choice questions, you may get this question that will this have oblique asymptote or not? The answer is no. It is a straight line with a hole at x equals to minus 2. Do you understand? So what you also note here is that we do not have any horizontal asymptote, right? So in this case, no horizontal asymptote and no vertical asymptote, right? And no oblique asymptote. Does it make sense to you? So this is a very important example where actually speaking, neither of these three asymptotes are there, but there is a hole, right? So that is what you should take from this question, correct? Now here we have a very interesting graph. Y equals to x over x squared plus 2. I could always write this as x over x plus, now, square root of 2, right? So we could write this as x plus square root 2 times x minus square root 2. Correct? Now that really means that we have two vertical asymptotes. So what are the vertical asymptotes? Vertical asymptotes are at x equals to plus minus square root 2, right? Now, degree of denominator is higher, so we have a horizontal asymptote, which is y equals to 0, correct? Why do we have horizontal asymptote? Because degree of denominator is higher. Is it okay? I'm not writing that numerator. And why do we have vertical asymptote here? Because the denominator is 0 for plus minus 2, right? So, because denominator equals to 0 for x equals to plus minus square root 2. Clear, right? So that is to say, if I have to sketch this graph, then it should look like what? So our sketches, as you can see, are very meaningful, but we're not wasting time in kind of accuracy which doesn't add to the value. So square root 2 plus minus, let's say these are my vertical asymptotes at x equals to plus minus 2, right? It has to be symmetric. Okay. So we have these two asymptotes which are at minus square root 2 and at plus square root 2, right? So if you take some values, let us say first value is 0. So what is x equals to 0 equals to? That gives you y equals to 0. So we get a point here, correct? Similarly, if you take x equals to 1, x equals to minus 1, you will get a point which is kind of like this. And so that part of the graph can be sketched as this. So sketching here really means that make a column. Is it okay? And take some x values and calculate y values. Correct? So you get the center portion. Perfect. So you got some values here. Right. Now what you need to do is that you need to substitute the values beyond square root 2 on the right side and less than minus square root 2. So this is a vertical asymptote. If you write a very high value, that is to say, when x approaches negative infinity, right? This is positive, that will be negative, correct? But 0. So y will approach 0 from the negative side. So we are going to approach from the negative side. Does it make sense to you? So the graph on this side will actually be kind of like this. So that is from end behavior. What we are saying this is called end behavior. So we'll try to see what happens when x approaches from positive infinity. If you approach towards positive infinity, both are positive, so y approaches 0 but from the positive side. So it is going to approach kind of like this, and the graph will be like 1 over x graph, right? But position is kind of shown here. So the type of graph which you get for this function will be as shown here. So what do we learn here? Now, important thing here, which you also learn, is that domain is x belongs to real numbers, where x is not equal to plus minus square root 2. However, the range is y belongs to real numbers because of the central portion. Do you see that? There are no restrictions. So in the range of a polynomial, at times you may not have any restrictions, right? And you also see that we have two vertical asymptotes and one horizontal asymptote in this particular case. Now, as a question, let me give you a question here. The question for you is to find increasing and decreasing interval. So your question is to find increasing and decreasing interval. Now you see, you have to check from left to right. So what do you note here? It is always decreasing, right? So it is always decreasing in its domain. Perfect. Domain means this portion. So at times you can say from minus infinity to minus square root 2 union, from minus square root 2 to plus square root 2 union, from square root 2 to infinity. Do you understand? So it's always decreasing in its own domain. Perfect. So in this part of this rational function, we also learned about increasing decreasing interval. Correct? Now, another very important thing which you get from here is about the symmetry. So that is very important to check what type of symmetry this has. Now this function is, you will notice, symmetric about the origin. So if you see from the origin, it is symmetric, right? So this particular function is symmetric about its origin, and this symmetry is called odd symmetry. Now this is extremely important. So not all functions have this kind of symmetry. 1 over x is one example, but here is another one for you. Okay. Algebraically, you will notice that, let's say we call this as function f of x. In that case, f of minus x is equals to minus of f of x. Do you understand? Now we just wrote it in very short, but look into my videos on odd and even symmetry to understand this concept. But as you can see, it is symmetric about the origin, and if you calculate, replace x with minus x, it will be negative of this function. So f of minus x is minus f of x, and therefore it has odd symmetry. Perfect. So till now what we have learned is about horizontal asymptotes, vertical asymptotes, holes, symmetry, interval of increasing and decreasing, domain and range. Perfect. Now we have two examples where we are going to understand oblique asymptote. Now we have a very special rational function. We need to understand the characteristics of this particular function, y equals to x squared plus x minus 12 divided by x plus 2. Since the degree of numerator is higher than the denominator, we have oblique asymptote, right? Now we'll learn how to find equation of oblique asymptote in this particular video. So what we do is we perform division. We have to divide the numerator by the denominator. The numerator is x squared plus x minus 12. Denominator is x plus 2. So if you divide, you can multiply by x. We get x squared plus 2x. So the idea is to get rid of the first term, the leading term, right? And then follow the sequence of division. Now you subtract. When you subtract, you get minus x here, x minus 2x, bring down minus 12, and this could go minus 1 time. So minus x minus 2, and that gives you, when you take away, you get minus 10 as your remainder. Correct? So that ways I could write my function y equals to the quotient, which is x minus 1, plus the remainder, which is negative here, 10 over x plus 2. You get an idea. Correct? So that becomes my form of equation, right, where we get this as my oblique asymptote. So now let me sketch and show you how actually it should look like. So the equation of oblique asymptote is this part, x minus 1, right? So the oblique asymptote here is y equals to x minus 1 is oblique asymptote. Okay, so let me sketch this, x minus 1. That means kind of like this. Correct? Where the y-intercept is minus 1. You get it, right? So we get the oblique asymptote. Now let's also look into this function and factor the numerator. So product of minus 12, sum of 1, 4 and 3. So we could write this as x plus 4 times x minus 3 over x plus 2, correct? So that gives you a couple of things. One, that we have x-intercept at minus 4 and at 3, and vertical asymptote at x equals to minus 2. So at minus 2, let me draw a vertical asymptote first. So this is our vertical asymptote. We'll call this as x equals to minus 2, which is the equation of vertical asymptote. Right. So we have here our oblique asymptote. Let me write OA, oblique asymptote, as y equals to x minus 1, and that is our vertical asymptote. Now we have two zeros also. These zeros are at x equals to minus 4 and x equals to minus 3, correct? Now this particular equation will be, if I write y0, this is 1, right? This is 1. So mine, this plus 3 will be somewhere here, right? So let's say this is 3 for us, and minus 4 will be on the left side of this. So this is minus 2, so this will be minus 4, correct? So we have this vertical asymptote and this oblique asymptote. So what you see here is that the function is going to approach this, right? Now when I say y, we could also write this as, let me rewrite, x minus 1 minus 10 over x plus 2. Now if x is very large, positive infinity approaching, in that case y approaches x minus 1, correct? Now it is minus, that means from lower side. So I'll write minus means from below, right? So means like this. Do you understand? It's approaching from below. So this part of the graph will look like what? This part of the graph will look like what? So here it is going to go down from here, kind of like this, approaching this value. Do you see that? X-intercept at 3. You get an idea. Okay. Now also see what happens when x is very large but negative. If it is negative, that becomes positive, right? So y approaches the line x minus 1 but from above, because this becomes positive. Is that clear? So on the right side, what we get is a function which will be kind of like this, where this line will be parallel to this as it approaches. Okay, so that is how the graph is going to look like. You get an idea. So I would like you to, in this particular case, also write down domain range, right? So clearly what we have here is that x is not equal to minus 2, correct? Range has no restriction at all. As you can see, the function is increasing in this part and there also. So it is always increasing in the domain, right? So it is increasing from minus infinity to minus 2 and thereafter, correct? So thereafter means from minus 2 to infinity, correct? So that is how it is going to look like. So I hope that makes sense. So this part is clear. Now I would like you to answer the last question yourself. Here is a similar one but with different numerator values, correct? Now the last example, I'd like you to pause the video, take this as your test question. Okay, so let this be your test question. We're talking about y equals to x squared minus 3x minus 4 divided by x plus 2. Now clearly what we have here is 1 degree higher for the numerator, so we have one oblique asymptote. Let's factor the numerator. So minus 4 means and sum is minus 3. So that means x minus 4 times x plus 1 divided by x plus 2. Of course, x is not equal to minus 2, correct? So that means we have a oblique asymptote, we have a vertical asymptote, right? So let me write down vertical asymptote, which is clear at x equals to minus 2, and we have x-intercepts, which is at x equals to 4 and x equals to minus 1, correct? So these things are clear. Now how do we find oblique asymptote? As we did last time, you need to do division. So divide the numerator by the denominator to get your equation for the asymptote. So that's the concept, correct? So if you divide, what do you get? We have x squared minus 3x minus 4 divided by x plus 2. So times x will give us x squared plus 2x. When you take away, you get minus 5x, and here is minus 4. Multiply by minus 5, we get minus 5x minus 10. When you take away, we get plus 6. So that means I could also write this as y equals to x minus 5 plus this time 6 over x plus 2. Okay? So that is another form of the same equation. And clearly, our oblique asymptote is this part. Y equals to x minus 5. Correct? So if I have to sketch, how will it look like? So let me sketch it right here. So we have oblique asymptote, which is x minus 5. Let's say this is our oblique asymptote, right? So let me just sketch it kind of like this. Okay. So at 5, y will be 0. That means this point here is 5. And this point here is minus 5. Correct? So this equation is y equals to x minus 5. Clear? Then we have vertical asymptote at 2. So let's sketch this. Let's say this is your vertical asymptote at 2. Okay. So the equation here is x equals to minus 2, right? That gives you the vertical asymptote. Now two zeros, one is at minus 1, which will be right there in the center, the other one at plus 4, closer to this place. Now, if you take x equals to 0, what do you get? You get minus 2, right? So at x equals to 0, you get minus 2, which will be kind of here. So approximately, you could sketch a graph which will look like this. Correct? So because we know at x equals to 0, y is equal to, if you plug in 0 here, we get minus 4 over 2, which is minus 2. Is it okay? So that is how the graph is going to look like. Now we'll learn later how do you find these maximum minimum points. Now on this side, we know it has to approach minus 2 as the value is, let's say, on the left side. So you can take a value for minus 3. So if x equals to minus 3, in that case, this will be minus 7 times, this will be minus 7, and that will be minus 2. And minus 3 will give me minus 1 here. So when you divide, you get negative 9, right? So negative 9 you get. So at minus 3 you get negative 9. You are somewhere here. So the graph will look like this. Okay, so that is how this function will look like. So take some values to figure it out. That's what I'll say at this stage. Okay, so at this stage we are basically learning more about asymptotes, less about curve sketching. So curve sketching is limited to plotting values. So take some x and y values, plot and then get. So what do you observe here? You see that we have an oblique asymptote, we do have a vertical asymptote, As far as domain and range is concerned, there is a restriction. For range, it's kind of difficult. So range is difficult here, which we'll learn later. How do you find some maximum and minimum value? So we'll make a note here. And note is to find local maximum oblique minimum. This is part of calculus. Is it okay? So we'll learn it in calculus, how to do it. At present, it is beyond our scope. So at present, what do we do? Approximate. So what do we do is take some x values and approximate. Okay, so that is, so table of values to graph. So I'd like you to take some values of x and then graph. You'll get a graph as shown here. So I hope that makes sense. Feel free to write comments and share your views. I hope the whole concept is clear. Now, based on this learning, I've designed few questions for you. Now, this is reverse working. Now, I'm telling you that we know that there is a hole and an asymptote give the equation. So the practice questions are kind of like this. Write an equation for a rational function with the properties given. So in the first case, I'm saying hole at x equals to 1 and vertical asymptote at x equals to minus 3. What should be the equation? Second, vertical asymptote at x equals to minus 2 and horizontal asymptote at y equals to 3. Third, an oblique asymptote at y equals to x plus 1 but no vertical asymptote. And the last one is vertical asymptote at x equals to 3 but the function is greater than 0. So these are your test questions. I'll provide you with their solution in the next video. And I hope you have understood the concept. With the concepts learned, you should be in a position to get these answers. Now here are solutions of these questions. The very first one is we are given two characteristics of a rational function. First, we are saying hole at x equals to 1. The second one is vertical asymptote at x equals to minus 3. Now the idea here is to understand both the concepts. When I say hole at x equals to 1, I could write the function y equals 2. Hole at x equals to 1 means we have two factors common in numerator and denominator. I mean, x minus 1 is common in both numerator and denominator. Only this, when they are common in numerator and denominator, that will give you a hole. Correct? The second one, when we say vertical asymptote at x equals to minus 3, it means that denominator is 0 for x equals to minus 3. So x plus 3 will be a factor here. So I hope you get the concept, right? So therefore, the answer will be x minus 1 over x minus 1 times x plus 3. Correct? So that becomes the solution of this particular question. I hope that concept is clear, right? So some of you may like to sketch this also. It will look like what? So when you sketch this function, basically, it will be 1 over x, which has been shifted 3 units left, right? So the vertical asymptote at x minus 3 means like this. And if I substitute 0 here, I get 1 over 3, which is positive. So that means my function should look like this. Right? And on this side, like this. Okay, now there's one catch. At 1, there is a hole. So we could write this as equal to, so this will simplify to 1 over x plus 3, where x is not equal to minus 3 and also 1, correct? Now if I substitute 1 here for x, I get 1 over 4, correct? So at 1, there is a hole here. Do you understand? So this hole is positioned at x equals to 1 and the coordinates are 1 and 1 over 4. Do you get an idea? So this point here is 1 over 4. So that is how you are going to sketch it. So the function will be sketched like this. With a hole at x equals to 1. Is that clear? Perfect. So that is how you're going to solve it. Now let's take the next example, which is write an equation of a rational function with the properties given. This time we are given vertical asymptote and horizontal asymptote, correct? Okay, so let's try to understand what are we given. So on a graph, we could actually plot these two. Horizontal asymptote at 3. Let's say this is the horizontal asymptote, right? And the vertical asymptote is at -2. Let's select this. That is the graph, correct? Now to get both these points, you could write the equation as y equals to, since this is y equals to 3, we know that if you write equation like ax plus b over cx plus d, in that case, a over c should be equal to 3. That's the whole idea. Okay. Now, vertical asymptote x minus 2 means cx plus d should be x plus 2. Only then you have vertical asymptote at x equals to -2, right? Now, since coefficient of x is 1, c should be 3, right? So we get 3x here straight away. Do you get an idea? Correct? So even this equation can work for us. So that could be one of our solutions. Do you get an idea? Now, if that is what you write, in that case, if I write x equals to 0, I get a positive 3 over 2, right? So at x equals to 0, I get positive 3 over 2, which is less than 3. Now here this is at -2, correct? So if I write -3 here, then we have both negative and we get a positive value. So make table of values to sketch the function, which should look like, well, from here itself, if I write 0 here, I get 3 over 2, which is less than 3. I get a graph which will be kind of like this. Well, and we have met both the criteria, correct? So our answer is right there. I hope you understand how simple it is, correct? Once the concepts are clear, it's not difficult at all. Now let's take the next one, which says oblique asymptote this time, x plus 1, but no vertical asymptote. No vertical asymptote is very important. Okay, that means we have y equals to x plus 1. We have to approach this value, but no vertical asymptote. So we could have like 1 over x squared plus 1. You understand? So if I have 1 over x squared plus 1, we are approaching a value, but we are not quite there. So that is how we could satisfy this. Is it okay? So this is how you should do it. Perfect. So the denominator is always non-negative, non-zero. Perfect for all values. So in this case, we have no vertical asymptote and there will be an oblique asymptote. Some of you can actually write this as x plus 1 times x squared plus 1 divided by x squared plus 1. If the question is to write in standard form the numerator and denominator, right? So you could do this. So that is x cubed plus x squared plus 1 over x squared plus 1, which could be written as x cubed plus x squared plus x plus 1 over x squared plus 1, correct? So that will give you the condition. However, this answer is good enough. So we'll just give that as our answer. Does make sense to you, right? Now here is the last question. I hope you're enjoying this series and you're able to understand how we are getting the equations from the given conditions. This time we are given that vertical asymptote is at x equals to 3. There is only one vertical asymptote and the function is greater than 0. It is always positive, right? So that is what it is, greater than 0. So in that case, a function which is always positive and the vertical asymptote is at a given point, think like this. At 3 we have a vertical asymptote. The function is kind of like this. It doesn't make sense. So that gives you an idea that the function could be y equals to what? Always positive means we have square. Only then it's always positive. And 3 vertical asymptote means x minus 3. Does make sense to you. So that is how you get your equations, right? So x equals to 3 is a vertical asymptote. So I hope that helps you to understand how to get equations for the functions when the conditions are given to us. Correct? So let's review them. So what we have here is 4 questions. When we say whole at x equals to 1 and vertical asymptote at x equals to minus 3, that means y is equal to, in the denominator we definitely have x plus 3, right? Since we have a whole also, we have a common factor x minus 1 in both numerator and denominator. So it's that simple. So in a multiple choice question, doesn't really take time. Part B. Vertical asymptote is given and horizontal asymptote is given. So since the vertical asymptote is at x equals to minus 2, the factor here is x plus 2. Since the horizontal asymptote is y equals to 3, we have to multiply this by 3 and write down, right? So it could be 3x, it could be 3x plus 1 minus 1, whatever, okay? Last question here, C is oblique asymptote is given, so write y equals to whatever the oblique asymptote is given plus no vertical asymptote. That means we don't want denominator to be 0. So it should be like x squared plus, it could be anything, right? So let's write 1 for example. It makes sense. You could write 4 also, it doesn't matter. Both are correct. Okay. Vertical asymptote is given to us as x equals to 3. That means x minus 3 is in the denominator. However, we are saying function is greater than 0. So that means it should be positive. Is it okay? So 1 over that could meet our criteria. So you could have actually answered this in just a second as we did here, right? So once you understand the concepts, it's become that simple. I hope it makes sense. Feel free to write your comments and share your views. And if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.